we're going to prepare for talking about Huffman coding by talking about Morse codes, frequencies, weighted average, and some basic concepts like that. So we are actually segueing in this course from data structures into algorithms. Okay, so we talked about data structures to hold and process large amounts of data. And now we're going to we finished talking about tries, and that's going to be our little segue. We're going to turn tries are a segue into Huffman codes, not Hamming codes. And that tries were a data structure, but they were used in a way to help remove redundancy. And it was even in a tree format, and that's going to be our segue into Huffman coding. Okay, so all that said, that's of course Morse code for SOS. The only Morse code you should know, but it's worth knowing that. And in Morse code, every letter is represented by either dots or dashes, a series of dots or a series of dashes, or both. So Z, for instance, is D D D D, da da dit dit. Q would be a D D D D. Short letters are used a lot, are very short. T is simply a D, and A is a dit. So we can actually look at various, the entire Morse code there. And of course, this was, Morse code was invented way back when. This is somebody sitting on a telegraph wire. You can only they sent a simple voltage over the wire, either a 1 or a 0 over time. And they came up with this particular encoding. And you'll notice that, yeah, some things are really short, like E. It's not used very much, while Z and Y is pretty long, letters that aren't used so commonly. And that's intentional. You can save time that way, right? So, okay. So let's go back and compare that to, by the way, how many bits do we need to represent 26 different letters if we used a fixed length encoding? Here's another way to ask that. How do computers represent the letters A through Z, and how many bits do they need? Well, Latin 1 uses 8 bits per character. Okay, so every single character, and that's actually more than A through Z, right? That's upper and lowercase, punctuation, all sorts of a bunch of special characters in the upper range. How about just A through Z? If we go and look up the ASCII chart, I haven't thought about doing this, but here and say man ASCII and get a chart. If I look at just A through Z, we'll look at it in decimal. This table reads top to bottom. It's kind of weird. No, it's reading left to right. Okay. A, capital, let's go to small letters. Here we are. Small a is 97. Let's look at capital letters. Capital A is 65, B is 66, C is 67. And they go from 65 up through, 90 here for Z. How many bits do they use? Well, if you look at that, all the letters start, if you think about the bit patterns for 65, that's 64 plus 1, right? So that's the bit pattern 1, 0, 0, 0, 0, 0, 1, something like that. And so actually, if you are 1, 0, 0, 6, the bit pattern for 64, 1, 0, 0, 0, 0, 0, you're sitting there and add anything to that, you get the letters A through Z. And so really their 6th bit is the 1, indicates, hey, I'm about to start a character. And then the remaining 5 bits are your characters, something like that. 7th bit. It's a little bit, actually, if you look at it, uppercase and lowercase are the distance from capital A to small a is exactly 32. Why is 32 interesting? It's a power of 2. Actually, the way, if you look at the bit patterns for A through Z, uppercase and lowercase, you have one bit saying, hey, I'm about to start a letter. Another bit saying, hey, is this an uppercase or a lowercase letter? And then the remaining 5 bits are which letter do you have? So really, here's what I'm trying to get at. It's taking 5 bits to store the 26 letters, right? We need a power of 2 that's bigger than 26, so 32. And then we actually have a few. We have 6 left over, so we can store some different punctuation and so on in there. So after A through capital Z comes square bracket and slash and a few characters, and then you pick up with the lowercase letters exactly 32 later. Okay, so fixed length encoding would need 5 bits per letter. If we want to do all the punctuation and the special characters, yeah, we'd use even more, maybe 7 or 8 bits. And I'm not even going to mention Unicode and UTF-8. UTF-8 is a pretty neat encoding if you look into the details on Wikipedia. But, okay. So anyway, great. Yeah, we can go ahead and have Morse code here. Here's my question. What's the average length, number of symbols that I need per character on average in a Morse code message? So you could just go to this table of Morse code and say, well, okay, A takes 2 symbols, B takes 4 symbols, C takes 4 symbols, D takes 3, E takes 1. You could add it up and divide by 26, but that's a little bit unfair. Why? E is used a lot in the English language. It comes up a lot. And your average message length, I didn't say the average length of a character. I said the average length, number of blips in a message, okay? And in a message, E comes up a lot, and Z and Q don't come up so often. So, gosh, yeah, what we should do is take a particular message, add up all the Morse code blips in that message, and divide by the number of letters in the message, the number of English letters in the message. That would give us the average number of blips per English letter in a particular message, except what message? You know, SOS is one message, a very short one, along with yee, a mouse. That has 93 E's at the start, and that compresses pretty well. While the snoring person, zzz, that has a lot of blips per message, or per character, per English letter. So what we really want is a weighted average. Here's what I'm going to do. I'm going to take an average over all the messages. All the messages. Here's what I'm going to go and find a corpus of English language. I'm going to go and look at, I'm going to take the collected works of Shakespeare and every comic book episode written down, and grab a whole bunch of different large works, take all the text of Wikipedia, and I'm going to go through and say, hey, how often does A occur? How often does B occur? How often does C occur? And then I'm going to use that and say, on average, a message that comes up in the future, if E is used 12% of the time, well, in a future message, E should be used about 12% of the time. So, okay, let's use that as our letter frequency. And by the way, you can go and look up letter frequencies. If you look in English, E is used about 12% of the time. They went and found 40,000 words, a sample of 40,000 words, not just the first 40,000 words in the dictionary. That wouldn't be representative. Some words are used a lot more often than others. So they looked at 40,000 words actually being used in a whole bunch of emails or whatever. Yeah, E occurs 12% of the time, T 9% of the time, A 8% of the time, and so on. All the way down, Z is the least commonly used with 0.07% of the usage. So Q is near the end, J, Q, J, Z, all very seldomly used. By the way, a little trick if you're wanting to remember common letters, you're off playing Wheel of Fortune, like what letter should I guess at the start? Let me just guess a common letter. You can memorize E-T-A-O-I-N-S. I find as a very good benchmark the word creations. That's full of all the common letters, the most common letters. So, okay. Well, now let's get back to our question of, hey, for Morse code, how efficient is Morse code? Okay. And what do we need to know? The frequency of A is 8%. So I went ahead and copied the frequencies of the, I'm just going to worry about A through E to do this computation. Come on, let's face it, the other 21 letters, not that important. So A is dit, B is da, dit, 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 C, D, E. Let's go look up those. And again, why am I having us look up these? Da, dit, da, dit. I want to just sort of emphasize how the designer of Morse code went ahead and said, hey, I'm going to make common things be short and uncommon things be long. E is simple dit, and a D is da, dit, dit. Da, dit, dit. Just a dit. Okay. And let me do a copy and paste of this right now. Okay. So, gosh, what do I need to know? How many blips? I made up the word blip, but meaning a symbol, kind of like a bit, but for Morse code. 4, 4, 3, and 1. And I'm just going to go ahead and call these the relative frequencies. These are not, since I'm only using the letters worth speaking of. Yeah, these don't add up to 100%. That's okay. Let me go ahead and take the weighted average. Okay, so how do I take the weighted average? A takes one blip and occurs 8.12% of the time. And B takes 4 blips, occurs only 1.49% of the time. C takes 4 blips, occurs 2.71%. Okay. Now, if I did all the letters, I could just compute this to add up to 100%. I'd basically divide by 100, and I'd get my average number of blips per letter. Okay. As it is, I'm only taking these letters, so I need to sort of normalize this by, hey, what is the total weight of all the letters? Frequency of all the letters is just add up those frequencies there in the denominator. And this, we'll call this the weighted average. But again, why is it the weighted average? It's because, hey, I went ahead and took a message that was, say, a real message which is 100 characters long, and A occurred 8.12, B 1.49. And so, yeah, really, out of those 100 messages, I'm adding up 8 A's and 1.5 B's and about 3 C's, and I'm adding all those up and dividing by 100. So that's the original average, right, in a particular message. We're abstracting this out to a weighted average by saying, hey, I'm not talking about one particular message anymore. Okay, so if you go ahead and do this calculation here, you can get the average number of blips per letter. Okay, so I don't trust myself to actually type that into a calculator. I'm going to make some mistake. In fact, I'm not even sure I made a mistake counting up the length of each blip there. Let's go ahead and do a quick program, because heck, why not? We're on YouTube. They're storing the video length for me. I don't need to worry about that. So let's go ahead, and I'm just going to make this so that I can go ahead and put this into a program easily. I'm going to use a Lisp-like language. Oh, I need to do one more thing. I thought I could do this easily, but it turns out dot is a special thing in the language I'm about to use. So I need to go ahead and explicitly make this a string here. Otherwise it could be a symbol, and usually I don't have to do that step of quoting it. Okay, so let me go ahead and copy and paste the raw data. And why am I going through this? Just you should be able to sit down and write a little quick program, maybe using Python, maybe using some other language, whatever you like. But it's nice to be able to do something like that. So let's go ahead and define frequencies to be a list containing, paste in all that. Oops, did I get that right? There we are. Okay, I have a list containing, I put parentheses because I want to group each of those things together. A, 8.12, and a dot, those are all related. And the next 3 are all related, so I make that explicit to my language. If I were in Java, I'd probably make a whole new class to do that. That's very heavyweight. Here I'm just saying, hey, a list of length 3. So I have a list of lists of length 3. I want to go through, first I want to figure out the denominator. How do I get the denominator? I want to add up all those numbers. How do I get all those numbers? Gosh, I have a list containing lists of length 3, and it's the second item in the list is the number I want. If I have a list with 3 items, I can call second on that list and get that. If I want to use map, I can say, hey, go through the list frequencies and call second on every single item in the list. And what would we get back? Oh, it's just the list containing those 5 numbers. And then I can go ahead and I can say, hey, apply the addition function to that list, to everything in the list. So define denom to be apply plus to everything in here. Okay, so that's going to give us our denom. Okay, add it up to all that. Great. Now I want to go through and I want to take, hey, is frequency times the length of that string. So define a numerator. And what do I want to do? I want to go through, I'm going to build this up. I'm going to go through and map, hey, for every thing in the list in frequencies, here's what I want to do. I want to go ahead, I want to take a function that grabs the second item, grabs a third item, does a string length on that third item to figure out the number of blips, and multiplies that to the second item. So I'll go ahead and do this. Lambda, if you give me the info, the triple, not a best name, but I'll use it here. If you give me that triple, I want to go through and multiply the second item of the triple with the string length of the third item of the triple. Oh, great, thanks. My terminal window is goofing up its indentation over the line. Okay, map lambda, so I have lambda triple, that times that, close off. Now I should be using an IDE that tells me when my parens are closed here. Close off the string length, close off the multiplication, close off that lambda, map there, numer. That's not what I wanted. Oh, it is. Okay, 8.12 times 1. I see. Okay. Yeah, so let's just double check that. 1.49 times 4. Yes. 1.5 by 4 is about 6. Yeah, okay. Yeah, we're good there. So I want to go ahead and numer. Actually, I could maybe call that numer, so I goofed up a little bit. Here's what I do. I want to take, divide the sum of all those numbers, apply plus to the numerators, divide by the denominator, and that should give me my average. So 1.75. For the letters A through E, Morse code uses about 1.75 blips on average. Okay, so a little bit less than 2 blips. More than 1. Can't really ever get better than 1, right? But less than 2, that's pretty good. That's not bad. That is not bad. Okay, so now back to our notes here, and let me go and get back to the human table that has that hand-calculated number of blips. What did we say it was? 1.74. Okay, so that's the weighted average. And if you look at it closely, actually, could Morse code do better? Gosh, C was 4 characters long, but if I look at C and D, C is only occurs 2% of the time. That's not that bad. D, Actually, let's look back at our notes. Yeah. Could I do better? I'm like, yeah, if I take something, A was really short and E was really short, that was good. D was shorter, C and B longer, yeah, because they were rare. Yeah, that's pretty good. It seems in the ballpark. The most common letters are really the shortest, and A and E are just like much more common, so they're much shorter. Okay, so that's on the ball track. Can we do better? And that's what Huffman coding is going to give us. It's going to actually give us the optimal way of doing this. So first, just since I'm talking about Morse code, one problem with Morse code is if you hear a deet, 5 blips, 5 dits in a row, what could that be? Well, it turns out that's kind of ambiguous. It could be an H is 2 blips, so it could be EH. It could be HE. Okay, E is a single blip, right? So it could be E followed by S followed by E. Remember our SOS. So yeah, gosh, it could be E. It turns out in Morse code you don't actually have 2 symbols, di and da. You have di, da, and then there's a pause, and that's really important to separate the letters. Okay, so just be aware of that. By the way, some terminology. We'll talk about the plain text being the original message. Okay, the original English word. The encoded text is, hey, I've encoded this message as dits and das. I've encoded it into Morse code. So the encoded text is the Morse. So I can talk about the length of the encoded text, the length of the original text, or the ratio maybe, things like that. Okay, And by the way, just code versus cipher. In general usage, those code can sort of mean both. And computer science will try to say, hey, an encoding is just one way of representing information. And there isn't no connotation of secrecy associated with that, like there is in English, or can be in English. So a cipher will be, or an encryption scheme will actually have secrecy. I don't want people to be able to reverse engineer it if they don't know how. Whereas things like Morse code is meant to be decoded, is meant to be public, is not meant to be secret. Zip codes, I'm encoding a geographic region as a 5-digit or a 9-digit number. And it's not meant to be secret at all. It's just a way to encode geographic regions. So, okay. Okay. By the way, I don't like the fact, I'd like to stick with 2 blips, 2 values, maybe 1 and 0, and not have space be a third, a ternary alphabet. So I'm going to go ahead and use just 0s and 1s, and we're going to have to worry about the fact that, hey, spaces are going to be their own thing. So, okay. And I want to now introduce the idea of a prefix tree. So a prefix tree says a dot is going to be a node of the tree. And here might be a tree where, if I go off to the right, I hit the letter E. If I go to the left, I hit another branch. A couple branches there. If I go left twice, I come to a branch. If I go left 3 times, I end up with A. So A might be 3 lefts. T is 2 lefts and a right. And E is a single right. The nice thing about this, I'm going to go ahead and call left 0 and right being 1. So T I'll represent as 0, 0, 1. Yeah. A will be 0, 0, 0. E will simply be a 1. Now the nice thing is, if I go ahead and give you a string of 1s and 0s, okay, so let me spell out the word E-T, E, A, oops, E, A, T, and then another 2 E's at the end of it. Okay, if I give you this, you can walk across this string left to right, and you don't know where you are, but I'm sitting at the root of the tree, and I go to the right. Ah, that's the letter E, and you know right away, hey, I've decoded E. Now go back up to the root, and I go left, don't know exactly yet, but I know it's not E. Go left again, go left again. Oh, hey, 3 lefts brings me to A, so I can go ahead and know that I'm sitting at A. Then go back up to the root. Left, left, right brings me to T. Okay. And so the nice thing about having it in this tree format, it has the principle that is called prefix free. One keyword is never the prefix of another, okay? That was not the case in Morse code, where dit was E and dit was H, and dit was S, and I'm like, if I see a single dit, I don't know, gosh, now it's ambiguous. Have I reached the end of my letter or not? These trees, or these prefix-free codes, are nice. You can just take a prefix and you know exactly where you are. You just walk through it and you know exactly when a letter is ended. So we like that property. So, okay. So now we're at the question, what's a better than Morse code way to encode the letters A through Z? We already saw that ASCII uses, if you stick to just A through Z, it's 5 of the bits out of the 8 for an entire character. Okay. Well, should we put the most common? We want to make a tree that's really good for English that gives very short keywords for common letters, long keywords for uncommon letters to make our overall average, our weighted average, be small. That's what we're looking for. Morse code does okay, but it's not a prefix code. So once you add spaces, it is a prefix-free code. But I want to stick to 2 things. So, gosh, maybe we can put the most common letter at the root. Well, that would be E. Put E at the root. Gosh, that means if 1 is E, that means every other letter needs to start with a 0 followed by other stuff. And it turns out that's not the best way to do it. E is common, but it's not so common it should be really up right at the root. Okay. Think of what the tree looks like for ASCII, by the way. That's a perfectly balanced tree. It's a tree where you can look at, 0, 0, 1, 0, 1. After 5 bits, you know exactly where you are. Every letter is exactly 5, a height of 5 from the root. So that's a perfectly balanced tree. Doesn't take into effect that some letters are more common than others. Putting a letter at the root is probably too much, okay? So let's go ahead and we're going to come back and talk about Huffman coding and see an optimal way of doing this. That's pretty cool.